This is the recording for the second day of section 5-6 for our crazy little MCA schedule that's coming up this next week. We have section 5-6 about the law of cosines, and I had mentioned I just love this formula. You can't use it all the time. Like it says, we'll be able to understand and use the law of cosines to solve triangles given either the side angle side or side 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 situation. And then we'll find the area of triangles given side angle side or side side side, and we were introduced to a couple of really cool formulas to help us out with that. And today is apply the law of cosines to real world applications. So that's really our objective here. You know, we've learned all of the formulas. We talked about the law of cosines, which is what you see in the big blue blocks here. And we used that on a few problems. And then we went ahead and talked about the area of a triangle formula when you have that side angle side situation, which again, you know, on the ACTs, they try to catch you and make sure that this is something you can do quick, which means you've seen this formula before, which means you are in an advanced math class, because this is technically not a formula that you see most of the time in geometry, unless your teacher has some extra time to take you through those things. And then, of course, we talked about Heron's formula, which can be used if you just have the side lengths of a perimeter in order to find the area. So that's another one that, you know, they'll take a look, put it on the test, and on the ACTs, if you don't know how to do this, again, they know you haven't been in an advanced class, because it's another thing that gets dropped from most geometry courses when there isn't time to cover it, because it's just considered an extra. So now, for section 5-6, day 2, here comes our real objective, these real life formulas. So this says a tunnel is to be built through a mountain. So we can see the mountain up here, and in red I'll go ahead and show you where that tunnel is supposed to be located at. And we want to check to see, is this a situation we can use the law of cosines for? And we have a side, an included angle, and a side. So that's our side angle side situation. And since we're looking for the length in the red here, that would be lowercase c, because that's opposite our capital C. So we're going to use our c squared equals a squared plus b squared minus 2ab cosine of c formula. Again, it starts and ends with our C, and then everything else will be the A's and B's. So let me give myself a little room down here, and we'd have 388 squared plus 212 squared minus 2 times 388 times 212 cosine of 82.4 degrees. And so what we would do is just punch in all that wonderful information there, and then we'd take the square root. So let me try out the new calculator here. I'll pause this and put this information in. One of the things I checked first on my new calculator here is that under mode, definitely in degrees, and then went ahead and punched all of this in. So 388 squared plus 212 squared minus 2 times 388 times 212 cosine of 82.4 degrees. Try and get it all the way over there so that you can see that, and enter. So that's what we have for c squared, is that good information. And then we know we're going to have to take the square root of that. So second square root of our answer. So that'll be our final answer. But now we do want to write down, you know, those intermediate steps as we go through there. So our 173,730.2 let me see if I can get everything up here at the same time. There we go, so that we can still see that and write it down. Not going to be able to see it and write it down. So I'll stop this and get that written down. All right, so we've got our c squared step there, and I rounded that to the 3 decimal places like normal. And then we'd show that we went ahead and took the square root of that in order 416.810 feet. And that's all off of the calculator. You know, the great thing about the law of cosines is this formula is absolutely great to use once you have everything in order. Now the next problem gets a little more involved. We have an airplane pilot who sets out from the airport on a heading of 20 degrees flying at 200 miles per hour. All right, so remember we're talking about from due north here. So this pilot, there's my little airplane there. My airplanes often look like flying fish. So I've got my little airplane, and 20 degrees is like bearing from due north, remember. So the pilot's taking off and flying at 200 miles per hour. Now, after an hour, it says he changes heading. So what we want to use there to show that distance is rate times time, which in this case is going to be 200 miles per hour times 1 hour. So that first distance is just going to be 200, which is really nice. So we're going to put a little 200 miles right here. And then he changes his heading. Doggone it. So from due north, now he goes to 40 degrees, and I know this isn't necessarily going to be completely accurate here, but this is going to be 40 degrees right here. And after another half hour on this new heading, okay, well, that helps us out again, because a half hour, 200 times a half, so rate times time, for the second distance is just going to give us 100 miles. So we've got 100 miles right here. And it says, what is his distance from the airport to home? Well, that makes it interesting, because if we could just figure out this angle right here, then we can use the law of cosines. So what we're going to need to do is just kind of think backwards about what's going on here. So let me make a sketch down here that might help us out a little bit with this, just changing the way everything is looking at this point. So what we had was the 20 degrees, that was the first part. And then there was the change to 40 degrees, like so. And now, instead of thinking about outside the triangle, I want to think inside. And what this tells me is that this angle right here would be 50 degrees from the x-axis up, because I already had 40 degrees taken care of from due north. But then I have to figure out, well, what about this whole 20 business? And so it would be better to draw my x and y axis right here, so that I can see what's going on. So let me change where that x-axis is located at, because now I have my 40, and I know that this is 50. And I know that this is 90 degrees. And I also know that down here somewhere was a little 20-degree angle from when they headed off first. You know, that was the initial heading. So then I think, okay, well, if this is 20, this is a vertical line, this is a vertical line, and these are alternate interior angles. So that has to be another 20. So, and that's really tough to see. I'm going to go ahead and put an arrow right here so you can see that 20 degrees. What I really need to do is add up my 90 and my 50 and 20 more. So 90 plus 50 degrees would be 140, plus another 20 degrees is 160 degrees. So now we can go ahead and use the law of cosines to find that missing side. And it doesn't matter what letter we use to represent it. I think I'll just use C again, since we did that with the last one. So C squared equals, we had our 100 and our 200. And then we'd have the cosine of our 160 degrees. So this is the same thing where we would go through and just punch everything in and find out what we have. So I'll pause this and get that calculator back up. So you can see I've got it punched in. 100 squared minus 2 times 100 times 200 cosine of 160 degrees. The zero's kind of cut off there, but you can see the answer that I had. And then we need second square root of that answer. Oh, and this one, my new calculator, already comes up with grouping symbols. So that gets us 295.952 miles. So let me get this back to the smartboard, which is awkward with all of these new settings. And we had c squared at 87587.705 approximately to the 3 decimal places. And then when we took the square root, 295.952 miles. So we have our triangle with 160 degrees right here, our 200 and our 100, and now we have the 295.952 miles. Now, good thing to do at this point, because there are more questions behind this one, would be to say, you know what, I'm going to store that, because it looks like in the future I'm going to need this. All right, so store we will in alpha x. And there we go. So the answer is now in X. And my other calculator had that STO for store in there, but this one's a little bit different. So now that's stored in there for anything that we would want to do. And the next part of the question, it has to be our next focus. And let's go back up and find out what else they wanted, because there was a lot more to this problem. So this one says he lands at his house. Now we want to know what's the distance from the airport to home. Already found that. In the morning, when he leaves his house in his plane to return to the airport, on what heading should he fly to get there directly? Okay, so what we want to know is, if he's at his home and he turns around and goes back, what is that going to be right there? Because that's a part of what we need to figure out, his heading to go back home. Now, that's not all of it, but that's a big part of it. So when we look at the information here now, we do have a triangle here that has enough information that if we wanted to, we could use the law of sines. And so let's go ahead and use the law of sines to figure out what theta would be. And get this to scoot up. So we have the sine of 160 over our nice 295.952. So that's going to be helpful that we stored that. And then we want to know what our little theta is going to be there. So the sine of theta over the side opposite that, which is 200, straight across from it. So we'll have ourselves a little proportion here, 200 sine 160 degrees divided by 295.952 equals the sine of theta. So what we're going to have to do to get the angle back is inverse sine. All right, so again, I'm going to stop this so I can plug all this into the calculator. All right, so if you take a look at this, you can see I have punched in 220 sine of 160 and then divided that by my stored information, and I get 14.729 approximately for that angle. So I'll get that back to the main screen and we'll write that down. All right, so approximately 14.729 degrees for theta, using everything all stored into the calculator. Just so that you know, if you didn't store and we use the 295.952, your angle gets a little bit off on this one. So we want to use that store feature whenever we can. All right, so now let's make kind of a hyper magnified drawing of what's gone on so far so that we can keep track of everything. But this time, let's look at it as if home is the origin here. So here's the first problem. If he's going to turn back around, we're going to have to add 180 degrees to something. Well, let's figure out what that something is. When he came into home, there was a little 40-degree angle that was formed here, and that was that last heading that he had. Now what that tells us is this would have to be 50 degrees. And then we had our little theta from our triangle would sit right here, and that was our 14.729 degrees. And then we have to figure out, really, for his heading, 180 plus this angle. And I'm just going to call that one beta in there. So what we're going to have to do is figure out what beta is and then add that to 180 degrees, which would mean we probably better store that 14.729 degrees. And if you're worried you're going to have to go back and do other calculations with our 295.9522 or whatever, you could store it in a different place. So why don't we store this one under alpha and maybe Y, so hitting the number 1 key there and enter, because we want this as exact as we can possibly get. So we had a 90-degree angle. We know we have to subtract the 50, and we know we have to subtract our little theta, which again I put under Y this time. So alpha, Y, enter. And that gives us 25.271 degrees. So we had 90 minus 50 minus theta to give us that 25.271 degrees. And now remember, since they're turning around and heading back, we have that 180 that we have to add on there. So we'll go back to our calculator, and the answer we just received needs to have 180 added to it. So 205.271 degrees. To return home, to return to, I guess in this place we're going to call it was an airport, so to return to the airport he came from. Not just any airport. Our calculations were to figure out where did he come from. So 205.271 degrees to return to the airport that he came from. So that was a good problem. There's a lot of good math in there. The next one, not quite as complicated, which I'm sure you'll appreciate because that was a lot to go through. So example 5, it says measuring a baseball diamond. The bases on a baseball diamond are 90 feet apart. We can see that in the drawing here that they've given us that nice little 90 feet apart. And the front edge of the pitcher's rubber is 60.5 feet from the back corner of home plate. That has also been given to us there. And find the distance from the center of the front edge of the pitcher's rubber to the far corner of first base. So, and stop this so I could go ahead and put all the math in here, because we do have a perfect system here for a perfect setup, I should say, for the law of cosines. You know, we've got our 45 here, and we have the opposite side that we're looking for, side, angle, side. There it is. So that's all we would need. So what we would do is go ahead and put 60.5 squared plus 90 squared minus 2 times 60.5 times 90 times the cosine of 45 into the calculator, which, like I said, I already did so that I could save a little time as I go through here. So 4,059.857 to 3 decimal places, and then we'd take the square root of that, and that of course would give us C. So we go back here and we write it down. C squared equals 4,059.857, and then we take the square root and we get 63.717 feet. And that problem, like I said, not nearly as complicated as example 2. So example 1 and example 5, not too bad here for the second day of section 5.6, where we're dealing with real life applications. So now, this problem looks like a monster. The good part is we have different parts, 1, 2, 3, 4, 5, 6 to this one. So Jim and Barbara are house hunting and need to estimate the size of an irregular adjacent lot that is described by the owner as a little more than an acre. With Barbara stationed at a corner of the plot, Jim starts at another corner and walks a straight line toward her, counting his paces. They then shift corners and Jim paces again. So they're still using Jim as the pace person here until they've recorded the dimensions of the lot in paces paces, as in figure 5.29. So down here, we have a drawing of what they've figured out by the number of paces that Jim makes. And so what they're really trying to find out is the person that told them what the size of the lot was being accurate. So they measure Jim's paces and they're about 2.2 feet, and they want to know what's the approximate acreage of the lot. So the first thing it says here is for step one, we're going to use Heron's formula to find the area in square paces. So we're going to use what Jim had in terms of paces to figure that out. And remember, Heron's formula deals with the semi-perimeter. So the first thing we have to do is find the semi-perimeter for each of these triangles as we go through this. Again, I thought just instead of boring you with the basic punch it in stuff, the semi-perimeter, I'm going to call this one triangle 1 and this triangle 2 down here, would be 112 plus 102 plus 86 divided by 2, and that comes out to 150. But I suppose so that I can print these notes off for somebody, I better write down what I just did again. So that's the semi-perimeter for the first triangle. For the second triangle, we would take 81 plus 112 plus 115, and then we would divide that by 2, and that semi-perimeter comes out to 154. So now we have the semi-perimeters, and we're going to go ahead and put this into Heron's formula. So for triangle 1, our area, and I'll call that area 1, is going to be the square root of 150. And then what we would do is go through each of those dimensions and take 150 and subtract. So 150 minus 102 would give us 48. And then we would have 150 minus 86, which gives us 64. And then we'd take 150 minus 112 and get 38. And we would go ahead and punch that in. And like I said, I don't want to bore you with all of that good stuff. That comes out to 4,184.543. But this is square paces, and this is just the first triangle. So now we need the second one. So again, I'm skipping the part where I'm punching all that into the calculator because I'm sure you are perfectly capable of doing that. Then we have to calculate the second one because these two triangles make up the total area. And that one had a semi-perimeter of 154. And then again, what we do is go through and subtract the 112, the 81, and the 115 from 154. And that gives us 42, 39, and 73 for each of those sides. And if you punch that in, we will get 4,291.200 square paces. So number one said use Heron's formula to find the area in square paces. We have to add those two together to get that. So we would take area 1 plus area 2, and that would be 4184.543 plus 4291.200, and the entire area of the lot would equal 8,475.743 square paces. Now that's important. I mean, obviously Jim's paces are different than anybody else's paces, so what we're going to have to do if we want to know that this is an acre is start converting this. And that's what number 2 says we're supposed to do. Way back up here, number 2 says convert the area to square feet using the measure of Jim's paces. So right now we have 8,475.743 square paces for Jim, and they want us to convert this into feet, square feet. So I think, well, what do I know about a foot and paces and as far as Jim's feet go? And it was 2.2 feet for one pace. So if I'm supposed to convert using square paces, I'm going to have to square this. So I'm going to need 2.2 squared, which would be 4.84 square feet. for each square pace. So 8,475.743 square paces over 1. Here's our unit analysis. We were doing this a while back. So paces are going to cancel out, which is exactly what we want, and we'll get our answer in square feet. And all we have to do is multiply those two together, top times top. So the area in square feet is going to be 41,022.595 square feet, which is a good start. But this was supposed to be about acres, so we have to keep going. And that's what they're going to have us do in step 3, is to say, okay, now, if there are 5,280 feet in a mile, now convert this into square miles. Okay, so let's do that. We have square feet over 1. I better rewrite it. Again, I don't want anybody that's just looking at the notes later to wonder where on earth this stuff came from. So pretty obviously, in 1 mile, they said 5,280 feet, but we're converting square feet. So we're going to have to square both of those, and 1 squared is, of course, just going to be 1. So we need 5,280 feet squared, and let me take a second and punch that in. So that's a monster, and hopefully, you can punch this in a little bit easier. Just using 5,280 squared on your calculator instead of having to have that whole thing to punch in. So with this one, we're going to have our square feet down below here. That's going to cancel out with square feet up here. But this is definitely division. So you're going to take 41,022.595 times 1 on the top, and then on the bottom, 1 times 27,878,400 on the bottom, and then divide 41,022.595 by 27,878,400, and we get 0.001471481 square miles, just giving you everything that I see there on the screen. And we go on to 4. Because 4 says, hey, once you have the square miles, now convert this again. We've got square miles. We want acres. We want to know whether or not they're being told the truth. So now we have square miles, and they tell us that there are 640 square acres in 1 square mile. Well, acres are a square unit. That's what they are. Acres are about area, so they're supposed to have a squared unit there. So we're going to take our little 0.001471481 square miles, and we are going to take that times 640 square acres over 1 square mile, because it's just called an acre. It's not called a square acre, but we know that acres have to do with length and width. They're two-dimensional. So when you do that, you get 0.94, 0.941749, 202 acre. So this would be approximately 0.942 acres, of an acre, I should actually put right there. So what does that mean? Well, that's what they want us to talk about in number 5. It says, is there good reason to doubt the owner's estimate of the acreage of the lot? Well, they said a little more than an acre. Yeah, if they measured Jim's pace accurately, there is reason to doubt their estimate. So yes, if Jim's pace was measured accurately, they should doubt the estimate. Which means they better take a closer look at this property, because if the person is overestimating how much acreage there is, then it's quite possible that they have overestimated some other pieces that are going to cost Jim and Barbara money. And so for number 6, it said, would Jim and Barbara be able to modify their system to estimate the area of an irregular lot with 5 straight sides? So they find a new property and it has 5 straight sides. And what they used here was a method of just turning a polygon into triangles and then using that to estimate the acreage. Now, there's a lot of math they did there, but it was good math, and yeah, it would be a good way to do that. So yes, they could separate any polygon into triangles, and they could use this to estimate that. Now, in reality, they would probably go to the county and get a printout of the well, they usually have an aerial photo that they could use to figure out the square acres, square miles, square acres, anything, you know. But again, square acres we just call acres because they are two-dimensional. So our objective was definitely met. We saw a lot of real-world problems here that deal with our use of our formulas that we've talked about in class. And again, I already showed you this assignment in class, but there's 5-6 day 1 and day 2, and this is the one that would have the real life applications in it for you to work on. So there it is, and hopefully we will be able to have class on Wednesday because we'll be done with the MCAs. So have this done when you come to class.